about software development, the process, oh, I'm sorry, lower right-hand corner of your screen, a little power switch. Do me a favor now, reach up, hit it, make your computer cold and dark. No glowing screen. That's okay. It hasn't left, it's just gone away for now. Fantastic. So as we go along in our software development process, we're talking about all sorts of things, and today we're going to talk about implementation, because that's a pretty good thing to talk about. So what's the goal of going through all this effort of developing software? Interesting question, right? I mean, it seems like you should have a goal, of course. And you know, ultimately, the goal is to deliver working software. You can deliver software that doesn't work, but who cares? That's not going to do anything. You can deliver software that doesn't have all the functionality that the customer wants, but that's not going to do them any good. So ultimately, your task as a software developer type of person is to deliver software that does everything the customer wants it to do. Implementation is a big fancy word that we say is what happens when you take what the customer says that they want and you actually transform it into working software. Okay? And there's a lot more going on here than just writing a bunch of code. Writing code is what we generally think of, but it turns out, and we have discussed all the other things that have to go on. You have to test it, you have to debug it, you know, if you're using depending on the language, you have to compile it, and then of course you have to package it into a deliverable product. I mean, it can run in the cloud, or it could show up on a CD or a DVD. It's got to have some documentation with it. You're going to have installation instructions. You're going to have a support program built around it. I mean, there's a ton of stuff, a lot more stuff than just that code going on here. So what makes a good implementation? Because anybody can implement stuff, but if you can do it good, that's even better. Readability. Can people read your code? Can other programmers pick up your code and understand what's going on there? Interesting question. Maintainability. Okay, great, I can read it, but can I figure out what's going on? And if I have to make a change to it, is it clear where I have to go and what I have to do? Performance. Okay, the thing should run as quickly as possible. If you created the best darn code in the world and it takes just under a year to execute, well, that's not really going to do it. Okay? Traceability. In other words, I have to be able to take a look at your code and understand which user story this piece of code relates to. Hopefully you've told me in your code. Correctness, especially if you're working on something, I don't know, like an air traffic control system, you know, it really has to be fairly accurate. If you're not accurate, all sorts of really bad things can happen. And completeness. Listen, as a customer, I ask you to implement 15 features. If you present me with a piece of code that implements 10 of them, that is equivalent to close but not quite. Okay? Now, the interesting thing is something that we often don't think about, because we look at these and we think, these are all good things. Yes, I'd like to have each and every one of those. Well, okay, that's fine. But one thing you have to realize is that each one of these is a trade-off. They require time, energy, and effort to implement. If I'm spending time here, then I'm probably not going to have as much time to spend down here. The big smoking gun generally is performance. I can do all sorts of crazy things and make my code run faster and faster and faster. But as I do those crazy things, what's going to happen is it's going to become more and more confusing what my code actually does. So I'm pretty much sabotaging maybe readability and maintainability to get higher performance, right? I'm using some funky coding techniques, or I'm reaching into the center of the computer and I'm using some sort of spare cycles to whatever. Okay, that's cool. But all of a sudden maintaining and reading that code is going to be just a pain in the butt. So is it worth it to get the performance out of it? Question, sir?
What's the big difference between traceability and readability?
Okay, so traceability says, listen, I can relate a chunk of code back to a user story. Okay? So user story number 15 that says I want to be able to order a DVD with my trip to my shack on a lake. Okay? Great. Where's that code? Bam! This is the section of code that lets you do ordering DVD. Readability says, hey, here's a chunk of code that allows me to order my DVD. Can I read through it and see what it's doing? Okay, I'm going to take the video as an input. I'm going to reach out to the video production house. I'm going to package it up. I'm going to ship it out. When it comes back, I'm going to have a receipt. I'm going to match the receipt to the order that I submitted. I'm going to make sure that the DVD then gets shipped to the person. I'll look at their receipt as to when they paid the bill. I'll get their home shipping address. You know, whatever the story is. Can I read what that code does? Can I understand what it is? Does that make sense?
Readability is kind of smaller bits. Traceability is the bigger chunks.
Yeah, so readability deals actually with the code itself. I can read it, and traceability deals sort of with the bigger picture that says, here's the requirement, show me the chunk of code. And it could be unreadable code. I can't read that code. But at least I can tell what code is associated with which users. That make sense?
Yep.
Okay. Programming style. Ooh, style? What? Yeah, no, I just sit on code, man. There ain't no dang style going on. But there is, sort of. Because in your homeworks, how did I tell you to start your homeworks out? What's the first line in each one of your homework?
Your name.
Your name. It's a homework assignment, right? I mean, it's sort of crude, but it is a style, right? I mean, there's at least that to it. And I've been telling you to put comments in there. I've been telling you to put, I yelled at you a little while ago and said, hey, put some blank lines in there, right? Separate out your code so I can tell the different parts of it, right? We're getting to style piece by piece, right? Okay. Pretty much every software organization will have its own coding guidelines. You go to work for anybody, they're going to say, hey, when you write code, this is the way you do it for us, okay? The coding guidelines are going to go over a whole bunch of stuff. Naming, indentation, commenting styles. Hey, comment everything. We don't really put comments in our code. We put 3 lines of comments before each function. Whatever the story is, they will have some sort of rule. And what they're shooting for there is they want all their code to sort of look like it was written by the same person. I mean, I might have a team of 100 programmers, but I want all the code that all those 100 programmers are doing to all pretty much look the same. And look good, of course. But I want to make it look, so that means when I hand code off to other people to fix or debug or something like that, they always know what they're looking at. Okay? A bunch of development tools can be programmed to implement these styles, which is sort of cool. In other words, you don't have to worry about that style that much if the tool that you're using to write your code automatically formats and indents and starts to do your variable names and stuff like that. God's honest truth, these style things aren't terribly important, and they are literally just style. They don't affect the code. They don't affect how the code runs. It's just really how it looks on a piece of paper. It's just a matter of you getting used to the style that's being used. You want to make it easier so when somebody comes back and takes a look at your code, they don't get confused. Your code looks like everybody else's code, and it's easy to understand and it's easy to read. Okay? Guidelines should cover things like error messages, right? So if something goes wrong in the program and you put out an error message, you can do the classic sort of Microsoft error message. Error number 2423, I died. Well, okay, that doesn't look so good. I wonder what has to go on. So, the question is if your program runs into a problem, what kind of error message are you going to produce? You will probably have a numerical code, because that's actually the clue to like the detailed programmers in-house. Hey, I was in the middle of this for loop here, and I died. Okay? But you'll hopefully have some text that's also descriptive to the user. Could not find file, could not open file, ran into a divide by 0 situation, ran out of memory, whatever. But you'll have some sort of message for the user that tells them what's going on and explains why things happen. Banning parts of a language that have been found to cause lots of problems is pretty common. Python, C, Java, they're big languages. There's lots and lots of commands and function calls and all sorts of stuff like that. And they're all probably very powerful, but a bunch of them can get you into trouble, okay? We didn't actually cover it in this class, but there's something called multiple inheritance, where you can cause one thing to be able to do different things depending on what kind of thing. If you're dealing with integers, it does one thing. If you're dealing with floats, it does something else, but it looks exactly the same. Fantastic and wonderful, very powerful, but man, you can screw yourself up quickly with that. So potentially you say, screw it, we're not going to use that. Depreciated language features, which means that things that are part of the language today, but the people who run the language have said, listen, this is going to go away in the future. Don't use it. Okay? So people then don't use it. You want to be able to compile with no warnings. Any warnings are telling you you've got some problems. Your goal for maintaining good coding style, it has to be consistent. Okay? And of course, you want people to understand what your code does. Simple stuff there. Coding style recommendations. Okay, cool. All right, naming. We've already talked about naming, if you like your variables and stuff like that. Okay, it's critical to improving your readability. Bad names. You use bad variable names, you're going to have to make up for it. You're going to have to make up for it by adding more comments. Sorry, I came up with bad names. So here's about 6 comments to explain what's going on. Good names means that people will understand what's going on. Interesting ways to go about doing things. A lot of times people use long names for global variables. So a variable that's being used throughout your program, use a longer name, a more descriptive name, maybe with a bunch of words stuck together. Index to student database for finding grades or something like that. Okay? Use shorter names for local variables. Okay? It means that if I see 2 variables together, depending on the length of the variable, I can tell you whether or not it's a global one or a local one just based on the length of the variable itself. Consistency is king. Use the same word for a given concept. In our homeworks, we used patient all over the place. We did not use customer. You know, if you're working in a hospital environment, you could view everybody who comes to a hospital seeking medical attention as being a customer. There's no problems with that. But if you're going to do that, you need to be consistent in your program. Don't refer to them as a patient in one place and a customer in another. And of course, if you have teams made up of people from different cultures or speaking different languages, you can run into problems real quickly because they will have a different way to reference or come up with variable names. So you can bump into some problems you'll have to work through. Separating words and capitalization. So we know that variable names are made up of words, and we know that variable names can be made up of multiple words, right? Index for student grades or something like that, okay? You can't use spaces in variable names, so you have to use something to sort of separate the words. You can just run them all together, but then that becomes difficult to read. Different languages have different conventions. In the language C, more often than not, what they do is they make everything lowercase, and they use an underscore to separate between different words. Once again, it's just what they got used to and started with, and generally that's what we find in the program. In Java, generally there's no separation, they use capitalization, sort of like we've been doing in this class for our variables, right? Is one better than the other? Absolutely not. There's absolutely no difference. Does the compiler or interpreter care? Does not even see it, right? It translates it into some sort of internal representation, and it does not care what you're using. It's really just more of a style thing than anything else. Indentations and spacing, okay, so we know that this is a critical part of Python. Your program will not work if you don't do this. But the question in Python is how many spaces do you use? Because all Python says is put at least one space to indicate that you're indenting it. What's interesting is I found the Google style manual for Python. Google says use 4 spaces when you're indenting in Python. Is there anything special about 4? No. Okay, absolutely not. That's just what they recommend. Indentation affects readability and maintainability, common styles should be followed. Consistency, 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 consistency. Okay? So that's the key thing there. Okay? Because really, once again, you want your code to look like code written by everybody else. Function size. So we know about functions because we've used them in homework 3 and homework 4. We know just a little section of code that you break off because you're going to call it multiple times. We've got no problems with that. It turns out how long that function is matters. Okay? And the reason it matters is because if you can look at a function on a single sheet of paper, it becomes a lot easier to understand what that function is doing. Get your head around it, right? If you have a function that extends over multiple sheets of paper, you probably made that function too long, and that's not good, okay? Because what they found is that longer functions generally have more errors in them, right? So about 50 lines of code, which turns out to be about the number of lines that you can fit on a sheet of paper, is how long each function should be. And it helps keep it, excuse me, on a single sheet of paper. But once again, it just makes it a lot easier for you when you're going to debug your program. Unique language features. Every language has their own little weirdo things going on, okay? You gotta be careful because you might misuse them, okay? If it has a go-to function in it and multiple inheritance, things get weird when you start using that stuff. So the recommendation is generally to stay away from it. You know, in Python, we've got try, exception, and finally. That's sort of weird stuff. If you need it, of course, use it. There's no question about that. But if you don't need it, then you're probably just going to end up confusing things by including that in your code. Comments. We love comments. Comments are a critical part of our program, so we can communicate to the grader what we're trying to do. Right? Okay. So comments are important. Comments can help or hurt a program's readability and maintainability. There's 2 problems with comments. Comments don't come without their own set of special problems. The first one is, if you put too many comments, I'm going to have to hunt for your code. You don't put comment before and after every single line? I mean, it turns it into a small novel, right? I mean, stop that. Comments are there just to help me. Oh, and the other problem with comments is they may be flat out wrong. In the next line, I'm going to go ahead and I'm going to add something to my list. Okay? No, you're adding 5. There's no list involved, right? So, for a wide variety of reasons, you may have changed your code, forgot to update your comments, maybe you were just crazy when you were writing it. Comments may be completely wrong. They're just going to screw up anybody who's taking a look at your code. Comments can also become outdated as code changes, which is a really critical thing. So as you go in to make changes to the code, you also have to remember to make changes to your comments so the comments line up with your code. The comments can be wrong from the start. You never execute a comment. You never run a comment. You never compile a comment. So your comments really, arguably, never get checked unless somebody takes a look at your code and comes back and tells you what's going on. There are 6 different types of comments. The first type is where you repeat the code, which is of no value to anybody. Generally, a comment like, oh, increment the index by 1, followed by a line where it's like index equals index plus 1. Oh gosh, thanks for that comment. That was really helpful. No, it wasn't, okay? Explanation of the code explains what complex code does in human language, and you would think that that would be good, but the problem is no. If the code's that dang complex that you need your comments, so the person who's reading your code understands what's going on, you probably should simplify that code. Maybe you use it as a marker in the code. This is really, really popular. Basically, hey, I'm going to come back and add some code here. I'm not going to do it right now, but this is like a placeholder for where something's going. That's fine. You just have to come back and actually do it. Summary of the code. Okay, comments that summarize what the code does. They're helpful. The problem here is that you actually have to keep it up to date. This is the most important one. Description of the code's intent. Okay, so you don't say what the code's actually doing, but you say what you want the code to be doing. So if I'm reading through your code, now I see what the code's supposed to do, okay, in like English language, and then I'm going to read the code, and the code's actually going to show me it being done. And then, of course, external references. If you're linking to something else or you're using an interface to another program or something like that, you can document what's going on there. Comments are a trade-off, okay? They can help clarify code related to other sources, so this is good. But you're sort of duplicating the code that you have. You should have clear code. I mean, arguably, you should not need to have any comments, right? Because your code is so crystal clear. Just by glancing at your code, I know exactly what's going on. Okay? Unfortunately, it takes time to create comments. And then, of course, just like having a baby, once you create comments, you're on the hook forever and ever to make sure that they grow up and that they're correct. Comment errors can be very hard to both find and correct. Goodness gracious, I'm going to correct your code, I'm not going to correct your comments. Unfortunately, you can do bad programming and then you hide it or cover it up by putting a whole bunch of comments around it and go, well, you know, I explained it in the comments, so it's okay, I can code that way. If you make really complicated code, you can surround it with comments with the hope that everybody will understand what's going on. So stop that, don't make complicated code. Arguably, you'd love to have self-documenting code. Code that's so crystal clear that really no comments are needed, right? Because people can just glance at your code, they'll know right off the bat what's going on. And that's a great goal to have, but nobody can really do it. So you're going to need to have some comments. You just want to make sure that your comments are, number one, correct, and they assist in understanding what's going on in your code. Debugging. Ah, jeez. If we didn't make errors, we wouldn't have to worry about them. So debugging ultimately is about finding where your code's going wrong, where something in your code's going on that either shouldn't be going on or should be going on, right? Right? We generally find problems with your code through testing. That testing team that's testing your code shows up at your desk one day and says, hey, we were running some tests and we discovered that there's something horribly, terribly wrong with your code. Alternatively, and far worse, is that users are using your code. And they come back and go, wow, that should not have happened. And they turn in a user complaint that says your code doesn't work correctly. Ah, darn, it slipped out, okay? By the way, debugging is a highly iterative process. You go through it, you make a change, you double check to make sure that you fixed it, fix, keep going back and forth doing this stuff. 4 phases in the debugging process. Very first thing is when somebody says there's something wrong with your code, you look them straight in the eye and you say, no, not with my code. My code has no errors whatsoever. And if you're lucky, you've scared them so much that they'll go away. Okay? And then you've got problems. Alternatively, if they don't seem to be leaving, what an annoyance. Come on, get off my back, man. It's not dragging me down. What you're going to have to be able to do is you're going to have to be able to reproduce the error that they're reporting. What were you doing when you did something wrong with my code? Okay, that's your question. You want to phrase it that way, right? Okay? So, you know, in some cases you're going to find the code works correctly. Yeah, I'm supposed to do that. Get off my back and go away. You're wrong, you're wrong, you're wrong. Okay? Unfortunately, that doesn't happen very often. Your goal is to write the simplest test possible, or set up the simplest scenario possible to cause the error to show up. Oh, okay. Yeah, no, it's really not supposed to do that. Okay? Once you've found it, to confirm that it really does exist, you want to localize in your code. Because you've written this much code. It turns out the error is right here. But you know, you got to take a look at all the code you wrote, and you've got to narrow it down to where that error is actually occurring. Okay? And this is really freaking hard to do. Because you know your code's not working, but you don't know where the problem is. Okay? If it's a simple test case, then maybe it gets a little bit easier to do. Now you got to correct it. Well, that seems like it's pretty straightforward. You figure out what's wrong, and you change your code so now it works perfectly. Or probably more appropriately, you change your code. You know, dear God in heaven, what did you just do to your code? Okay? If you knew what was going on, then hopefully you fixed it and you fixed it correctly. However, oftentimes people say, I think I know what's wrong, so I'm going to make a change to the code. Okay. Well, that's interesting. Maybe you just made another error. You know, if you make changes to your code without knowing what's really going on, the chances of you screwing it up more are very great. Verification is where you come back and you say, hey, listen, I've made some changes. Let me make sure that the changes I made fix the problem that was reported. Okay? You got to make sure that you didn't introduce any new errors into the code, and all too often, you end up not fixing the problem but actually causing other problems. Oh, jeez, it just keeps going. There's two types of errors in programs. There's something called syntax errors. These are the ones that you get a little red squiggly line from Python. It says, I'm sorry, you need to have a colon at the end of a trick question. You need a colon at the end of everything, right? Ors, whiles, ifs, pretty much the whole dang thing, right? So yeah, syntax errors are easy to find because the compiler is going to tell you. Logic errors are a lot harder, right? They're harder to find, and you actually have to understand what's going on in the code in order to be able to find it. Your bubble sort isn't sorting. Why? You're going to have to dig into that code to figure out what's going on. Debugging tools. You are not alone when it comes to debugging. Because debugging has been going on for so long, really bright, really smart people have made really powerful tools that if used correctly can help you do your debugging quicker, better, faster. Source code comparators. Basically, here's an old version of my code, here's the new version of my code. Compare it. Tell me where the changes are. Line 23, line 24, you change this, you change this. Cool, that's cool. Extended checkers, they find errors of syntax, logic, or style. So they'll go through and they'll say, hey, you got too much stuff in this if loop, or this if statement's inside of this while loop. Did you mean to do that? Interactive debuggers, those are pretty cool. They let you step through your code line by line, and you can display variables. So instead of all those print statements you're putting in, you can just set up all your variables, and then you can go step, 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 and you can see how the values have changed. That's pretty cool stuff. Specialty libraries. So if you're using a function that can screw you up sometimes, if you get a special version of that function, maybe it's going to protect you from making all the common mistakes. And there's something called a profiler tool, which describes pre and post conditions. You can run it, and it shows you where you're spending time in your code. This module, this module, this module, and this module. So you've got lots of tools out there. Assertions and defensive programs. There's things called preconditions, something that your code needs in terms to create correct results, good data. Post conditions, which says, hey, what should be the state of the world after your code runs? And then there's assertions, statements that check a condition and produce an error if the condition is not met. An example here is, listen, I'd like to withdraw some money out of my checking account. Fantastic. Let's take a look to see how much money is in your checking account. You've got nothing. Okay, great. You do not get to withdraw any money. Performance optimization. This is a tricky one. Okay? So we love performance. Everybody loves performance. Run faster, quicker, quicker, quicker. But the problem is when you optimize for performance, you're going to affect other things. If I can get my code to run quicker, it's probably going to become harder to read and harder to maintain because I'm going to do weird things. Now, the one exception to all this is real-time systems. In real-time systems, readability and maintainability goes straight out the window because it's all about performance. Once upon a time, I worked on the F-18 fighter jet, and you know we had performance issues like when the pilot pressed the red button, the missile needed to leave the aircraft. You couldn't go do some other stuff, you couldn't have a crash, you couldn't do anything. Really, the missile needed to leave the lab at the moment you pressed the red button. So that was a clear real-time constraint. Programmers often make the mistake of worrying about performance way, way too early. Hey, we're going to make this program, it's going to be great, it's going to run real fast. Okay? Stop. Okay? Number one, get your code to work. Don't sweat performance. Just get the dang thing to work. Okay? If you have problems with performance after you've created the code that works, go back and take a peek and look at it. What's interesting is that most of your code is only going to be executed like once. Okay? You can use one of those profiler tools to take a look at it. What you're going to discover is that only small parts of your program actually get executed a lot of times. So when you go actually to optimize performance, you really just want to focus on those portions of your code that are getting used over and over and over again. How do you actually go about optimizing performance? Well, you start with a profiler tool. Remember, this is like a third-party tool that's going to show you when you run your program, where is it spending its time? Wow, this function gets called like a whole bunch of times. Well, cool, maybe I should spend some time optimizing that function. Okay? What you do now is you review and you optimize only those modules that are going to cause you problems. After making changes, run the profiler again to determine the impact and ensure that the changes you made actually boosted your performance. You might make changes and they could improve performance, have no impact, or actually decrease your performance. So you want to double check to make sure that everything's good. But remember, optimizing things has a cost associated with it. Interestingly enough, if you're going to have a developer spend time working on optimizing your software, one of the challenges that you have is the fact that that's going to cost money. It's going to be that developer's time, so you can actually put a dollar value on how much you're going to spend trying to get your software to run faster. And the really cool thing is sometimes it's just quicker to buy faster hardware. Then your software can run just as fast as it wants to, right? You've got to weigh the increase in performance against the decrease in maintainability. So there's a bunch of things that you have to balance whenever you start messing around with performance. It's not cut and dry. Refactoring, we've talked about refactoring, okay? Refactoring is when I have perfectly good working code. Everything's fine, and I go back and I start messing with it again. I might be messing with it again because there's a better way to do it. Maybe I've changed my database. Maybe I want it to run faster. A whole bunch of reasons, okay? It's basically rewriting your code to make it better. Improves your code style without altering its behavior. That's the key point here. Don't break your code. Refactoring is one of the most powerful techniques for producing good code, and there's a bunch of different reasons to refactor: duplicated code, excessively large or long functions, and a whole bunch of other things. What do you do when you refactor? Well, you turn a code fragment into a standalone function. Okay, that's one thing you do. That's pretty cool. You can replace the body of a function with a new algorithm. I've come up with a better way to do a bubble sort. I can do it in 2 lines. Okay, cool. That'll be better. And you can move an algorithm from one function to another where it makes more sense. Stuck it over there, it really should be over here. And you can divide a function into 2 functions. Remember, we said functions should only be about 50 lines. You got that hefty 100-line function that's hard to maintain, hard to read. Maybe you go back in, you divide it up into 2 separate functions, and all of a sudden it's a lot easier to maintain. What did we cover today? Well, we talked about programming style. Because it's not just enough to produce code, you want to look good while you're writing it. We talked about comments, we talked about debugging, we talked about optimization, and wrapped up talking about refactoring. Whatever shall we talk about next time? Ooh, software support and maintenance. Remember, we talked about this before. 10-20% of your time is spent writing shiny new code. 80% of your time spent worrying about code that you already wrote. Seems like we should have a talk about that. Fantastic. Well, we can talk about some Python now. Maybe we should talk about what it takes to work with data. That sounds like a good deal. We're going to give you 15 minutes. Why don't we come back here at 9 o'clock.